So welcome back, everybody. And the topic this week is an actual discussion of how we actually write the VQE so that it can be applied on a quantum computer, the way we will do it. We are not going to use Qiskit. We are going to discuss in detail the three elements which we need to deal with. And that means that we need to look at something which is called the parameter shift rule for calculating gradients. We are going to look at how we perform measurements. And then we are going to implement the optimization part, which is actually the using the gradients and setting up measurements in the computational basis. Now, as you saw from the email, there are two Jupyter notebooks, additional ones, where I go through the calculation in a way you should do it in project one for the 1 qubit case and the 2 qubit case. So in a certain sense, and I don't hope you get offended, you will partly find the solution to the exercises B and the exercise D in the project. So we're going to do a short repetition. And as I say here, there are two Jupyter notebooks, and I'm going to go a little bit back and forth between the Jupyter notebooks, the notes here, and the whiteboard notes, so that we have all the ingredients ready for making the calculations. So quickly, the VQE as an algorithm is normally what we call a hybrid algorithm, and it results in what we call a parameterized quantum circuit. So this is a common denominator for many of the things which we end up doing in this course. Also, when we move to calculations of machine learning algorithms, to implementations to the solution of, let's say, differential equations, what you typically will have then is a set of parameters. You would initialize the system in some set of states. So you could have several qubits, which you initialize, and they could be initialized to qubit 0. That's a state. And then you would have an ansatz where you rotate and you perform linear superpositions of one qubit, the other qubit, etc. Then we can entangle with a C0 or a so-called CU gate, where U acts on one of the qubits. And this is a possibility which gives us a state which is entangled. And when we have done that, we have to transform back to the measurement basis, which in our case is going to be the qubit basis of 0 and 1. That's a computational basis. And there the Pauli Z matrix is the one which we need to transform the different chains of operators into a set of Pauli Z matrices. Then we perform the measurements on the Pauli strings. So every component of your Hamiltonian, so when we translate the Hamiltonian here, we are going to translate that one into a set of Pauli matrices. So it means that if you look at the blue box, which you have up here, where the arrow is pointing, we are going to rewrite the Hamiltonian as a chain of Pauli matrices. Then these are being transformed, and we perform a measurement here. So these calculations are done on a classical computer. And then we perform the measurements. We calculate then the gradients. These gradients, the blue box here, they give us a parameter update with a standard optimization algorithm, where you now can see something which reminds you very much of Newton's algorithm, except that we will typically have a fixed learning rate. So this parameter here becomes normally a parameter instead of us calculating the second derivative. So the ingredients which we are going to discuss today is, one, the rotation to a measurement basis. We obviously are going to repeat on how we set up the circuits. We are going to afterwards make the measurements. These are measurements which we will do again and again. So there will be a expectation value, a sample mean expectation value, which we then collect according to the number of experiments which we have run. Then, when we are done with that, we have the possibility to calculate the gradients. And this is the so-called parameter shift rule, which we are going to discuss today and look at the derivation of that one. Sorry. So this is essentially the overview of the VQE, which is an algorithm which allows us in principle to have a slightly smaller set of operations compared to one of the first algorithms which was introduced to find eigenvalues. And that's called the quantum phase estimation algorithm, which we are going to discuss a little bit later. So you will see that algorithm as well. So that means that when we have all these ingredients, then we are ready to calculate expectation values like that. So what I wanted to say now a little bit about what we did last week is that last week we did cheat. So we cheated because we performed these operations and then we simply calculated the expectation value. Also, in the optimization part, we called a standard minimization algorithm, which evaluated the derivatives numerically for us. And that's not the most efficient way of doing that. So last week, when we looked at the 1 qubit case, we simply set up this expectation value. We performed the rotations, we had the parameters theta, and then we calculated the derivatives with respect to the parameters theta, obtained the gradients, and then performed the optimization. So this is not the way it is implemented on a quantum computer. So the notebooks which we discussed last week, they were meant mainly as a way to take a bird's view on the algorithm here without going into those details which we see here. So what we did was to transform the Hamiltonian in terms of Pauli operators. We did this part, we did the answers for the wave function, but then we cheated here and we cheated here, because that's not the way it's done on a quantum computer. So I hope you see the woods for the trees, because it's there are slightly different approaches to the way you would implement it on an actual quantum computer. Okay, any questions so far? And the notebooks which you'll find this week, they actually do the measurements by rotating this or performing a transformation of the Pauli X matrix back to a Pauli Z matrix. And that means that there will be a different circuit for the calculation of this expectation value compared to the expectation value of a Pauli Z matrix and a Pauli Y matrix. So the different components of the Hamiltonian which you have, they require different circuits. So it sounds like a much more complicated problem than the one you've been used to before. So what you will typically see now, if we now stay with a 1 qubit case, and we are going to look at this in more detail, if you then think of the basis which we have chosen, the computational basis of 0 and 1, they are eigenstates of the Pauli Z matrix. So that means that we would typically then perform a direct measurement in the Pauli Z matrix. However, when we look at the Pauli X matrix, we have to perform a rotation or a transformation where we operate with a Hadamard gate on the Pauli Z and then perform another Hadamard operation. Similarly, when we have a Y gate, then we need to perform first a phase shift and then times a Hadamard gate, and then we can measure in the Z gate, which then allows us to find the measurements in the computational basis. So keep in mind that we have chosen a computational basis and we want to make the measurements in the computational basis. And the typical way you do that, if you then think of a superposition, which we have, it means that we would then count the number of zeros and the number of ones, qubit 0 and qubit 1. And the qubit 0 has a probability alpha squared, and qubit 1 a probability beta squared. And then the expectation values is estimated from normally what we call the number of measurements, or popularly called the number of shots. And the total error scales, so this would be the standard deviation, scales like 1 over the square root of the number of measurements for the number of shots. So the codes which we discussed last week, just to remind you of that, they did not include a shot-based sampling. So we simply evaluated the expectation value, and then we optimized that and performed the optimization algorithm, which is a quasi-Newton method, which was called COBELA. That's one of the possible algorithms for doing that. and then obtained the derivatives and did the optimization and found the optimal angles. But this includes, what we're going to do today includes an additional complication because we need to perform a set of measurements. So when you run a calculation on an actual quantum computer, you're performing the measurements again and again and again. So we need to bring in some basic elements of statistics when we do that. And in our case, that simply means to calculate the mean squared error. So also, just to bring up things here. So in the discussions last week, we used a quasi-Newton methods to find the roots of the gradients. And that means that we evaluated the gradients by a standard finite difference method. So we are going now to derive a more efficient way of evaluating the derivatives with respect to the parameters of a circuit. And these are the so-called rotation angles. And in order to optimize the VQE ansatz, we need to compute derivatives with respect to the variational parameters. And that's why we also call these calculations for parameterized quantum circuits, because we have a set of parameters. And we're going to optimize the calculation with respect to these parameters. When we are going to introduce quantum machine learning algorithms, we are still going to deal with a parameterized quantum circuit and then apply a specific machine learning method. So what we are going to do then is to develop first a simpler approach tailored to the 1 qubit case. That's where we're going to stay first. So I'm going to switch back to the whiteboard, if that's okay, and then slow down the pace a little bit because I want you to derive the parameter shift rule so that we have that one. So let's now do that and switch to the whiteboard. So a quick reminder of what we are going to do today. So we have a measurement in the computational basis. So that means that we are going to make a transformation both for the 1 qubit, the 2 qubit, and the many qubit cases. We want to make an efficient calculation of the gradients, and this is the parameter shift rule. And then we have the optimization part. So what I wanted to give you now is just simply the derivation of this so-called parameter shift rule, because that's the one we would implement when we are calculating the gradients of the energy. And we are going to use just the 1 qubit case as an example. And then we are going to move on to the 2 qubit case. And in the codes which you have in the Jupyter notebooks, this is actually implemented this specific way. Okay, so what we had for the 1 qubit case, let's take a quick look at that. What we have then is a Hamiltonian, which we can rewrite in terms of the different Pauli matrices. So we would have a parameter, which we just can call for A, multiplied with the identity matrix. We had a new parameter B, which is multiplied with a Pauli Z matrix. So this is actually a 2x2 Hamiltonian, which we then are tailoring to a 1 qubit case. And then we had a plus a C. So this is a very general transformation of a 2x2 matrix, plus D times Y. Now in project 1, we are assuming that the matrix elements of a 2x2 matrix, the Hamiltonian matrix, are real. So we don't have the Pauli Y matrix. But in the slides which you have and in the Jupyter notebooks, we try to keep this as general as possible. Now, so what we did last week was simply now to make an ansatz where we now rotate a initial qubit state, which we could set in the state 0, if we assume the system is in the ground state. And then we perform a unitary operation on that one in terms of an angle, theta, and phi. So we have two angles acting on 0, and that gives us a new state, psi of theta of phi. And this matrix U is a matrix now, which, and I have some additional notes in the lecture at the website where I actually discuss what are the constraints on this parameter shift rule which we are going to derive now. Because this is something which we cannot apply to all types of transformations. So this is something, this kind of parameter shift rule which we are going to derive for the gradients is something which applies to matrices of this type here, like the identity matrix. These are matrices, when you square them, they actually give you just the identity matrix. We know that the poly x squared, poly c squared, and poly y squared, they just give us the identity matrix. So I have some additional notes. If you want to look them up later, you can find some additional proofs about the parameter shift rule. So typically this one is now given by some rotation. We can write this as a rotation in the x and the y and the z axis. So we could have a rotation around the x-axis, a rotation around the y-axis. And this is then, that means that the new state, psi of theta of phi, is simply given by this Rx of theta multiplied with Ry of phi multiplied with 0, the initial state. And that is our ansatz for the state. And since it's a qubit, one qubit case, what happens then is that this state here is a general state on the block sphere. And for us then, since we are diagonalizing a 2 by 2 matrix, we know that the exact eigenvalue, since we are diagonalizing in this basis of qubit 0 and qubit 1, that is going to be a linear combination of qubit 0 and qubit 1. So when we then optimize the angles here to find the optimal energy, then we're also finding the exact solution. So this is the basic procedure which we are going to deal with. So if we now look at the so-called parameter shift rule, what we want essentially now is to find the following expectation value. So we want the energy, and what I'm going to do now is just to stick to one angle. But in principle, you can have many angles. So I'm just going to put up an angle which I'm going to call for phi. So what we are going to calculate is this expectation value here. You can obviously generalize it to more angles. This is what we want to optimize. And we need then to find the expectation values of this quantity, but we need also the derivative. So what we will need then is actually the gradient of this quantity here. And this is going to give us what is called the parameter shift rule. So let's take a look at these matrices which we have. So if we look at this Rx, Ry, I'm just going to label them, relabel them in terms of an Ri. And these are functions of an angle phi. So I could be a sigma x, a sigma y, a sigma z. And this is a transformation which is given by the exponential of minus I. And then I have the angle phi divided by 2. And then I have one of the Pauli matrices. So this is a transformation which we are going to do. It means that when we look at this as a circuit, the state 0 is now going to be transformed. So we can have a Pauli x, and we could have an angle theta. We could now have a Pauli y with an angle phi. And this is going to give us a new state, which we simply label as a psi of theta and phi. And this is a quantity which we then are going to use now to perform a measurement. So what we can note now, if we take the derivative of this dr of I of phi with respect to the angle phi, you see that this is equal to minus I divided by 2 times sigma I multiplied with the original r of I of phi. So this is an important property which we are going to use now when we are setting up the calculation. Okay. A small aside before we move on is that if we now look at the expectation values of the Hamiltonian, suppose we still stick to just one angle. So what we need then is actually to measure psi of phi, and then we have this variable A times the unit matrix. So this is pretty easy to measure. But then we need psi of phi, and then we have this B times Pauli Z matrix, psi of phi plus psi of phi. And then we had, let me just see that I'm setting up this correctly. So I have a C times X, C times X, and psi of phi plus, and then I have D times Y of psi of phi. So when you look at the two first ones, they are pretty easy to set up. In this particular case, since we now are having states now which are proportional to qubit 0, it means that when we perform these rotations, we will still be able to calculate these expectation values directly. However, when it comes to the Pauli X, we know that the qubit 0 and qubit 1 are not eigenstates of that one. So it means that we would have to transform that one. So this needs to be transformed now into a C times a Hadamard times a Pauli Z times a Hadamard. So what happens then is that if you look at this circuit which we are dealing with, we need to modify the circuit. So we will have one circuit for every component of the Hamiltonian matrix. So that means that for the circuit which contains the Pauli X, we would actually need to add a Hadamard here. So that means that if I look at this specific case here, and then I'm going to write a circuit for this one, so I would have the qubit 0, and then I would have a rotation here. Now I'm just looking at one angle, but I'm going to put in both angles. So I would have a Pauli X, and then an angle theta, and then I would have to set up a Hadamard rotation. And that would be my new state here, which I call for psi prime. Then I'm ready, if I have done that, then I'm ready to perform the measurement in the Pauli Z matrix. Similarly, if I have this one, I would have to transform that one into a phase gate times a Hadamard, and then I get a Pauli Z, and then H times a phase gate. So that means that I would have to increase this circuit, which you see here, with a phase gate as well, which I would plug in here. So every component of the Hamiltonian matrix is now rewritten in terms of its own circuit. Okay? It sounds very clumsy compared to what we did last week, where we simply just took the wave function and calculated the expectation value without thinking. But that's not the way which we would do this on an actual quantum computer. So when we looked at the derivative, there is also another thing which is useful to look at. If I look at these matrices, Ry of a given angle phi here, they are given by cosine, and it's easy to derive that. If you haven't done it, I invite you to do that. Minus I times sine of phi half multiplied with the involved Pauli matrix. That's a sigma I here. So what we are interested in now is to calculate the expectation value. And let's now look at the expectation value of just one of the quantities. So for every angle which we include in this parameterized ansatz for the wave function, we need to calculate derivatives. And the most general representation of a qubit is given by at least a rotation along the x-axis and the y-axis, or we could do the y-axis and the z-axis, etc. And that gives us a general vector on the block sphere. So what we need now is simply to calculate this expectation value here of phi of the Hamiltonian and then psi of phi here. And when you look at the expressions which we have for these derivatives, it means that we will have the derivative with respect to this quantity plus the Hermitian conjugate. Because if you look at this one and the vectors which you have, the transformations which we have here, clearly the brass side will have the Hermitian conjugate of this quantity. So that means that when we now calculate the derivatives, this is going to be equal to phi, psi of phi, and then we have the Hamiltonian multiplied with minus I divided by 2, and then I have the explicit Pauli matrix, which I'm looking at. And this is multiplied with psi of phi plus the Hermitian conjugate, because when I'm taking the derivative with respect to the angle phi, I have to take the derivative with respect to this quantity, which is given by the R here multiplied with the initial state. So this is essentially the quantity which we are interested in calculating. And if we now just look at we're just going to stick to the example with one of the angles. That means that the quantity we are calculating the derivative of is equal to qubit 0. If we have that as an ansatz, that's the most common ansatz which we have. Actually, if you want a challenge in project 1, you could try different ansatzes. Next week, I'm going to show you how the results can actually depend for the 2-qubit case on different ansatzes, especially if we don't entangle the qubits. Then you will see that we will get an ansatz which does not take into account the correlations properly. And that means that you will not get a state which is corresponding to the final state. Because without the entanglement, for the 2-qubit case, you will not be able to find the eigenvalues properly. So in our case now, what we have is simply this quantity here. We have an Ri of the angle phi multiplied with the Hamiltonian multiplied with Ri of phi. So if you now bring in more angles, the only complication is that you have more of these rotation matrices, and that's it. So when we then calculate the derivatives, what we see immediately is that this is obviously equal when we calculate the derivative. So let me just use a shorthand for this. I just call this for the expectation value, and I'll use the standard physics notation. So what I need then is this quantity here. So let's just do that. D of phi. And that is going to be equal, since I know what the derivative is like for this quantity here, which depends on the angles. And then I'm going to have the Hermitian conjugate. So what I'm getting then is simply phi, or psi of phi. And then I'm going to have h, and this is multiplied with minus I divided by 2. And then I have the Pauli matrix. And then what I'm having is that this has to be multiplied with state phi here, because this is nothing but Ri of phi multiplied with 0. And then clearly I have the Hermitian conjugate. We should not forget that one. So the question now is, how can we actually simplify this expression here, find an efficient way of calculating it? This leads to the parameter shift rule. So let's do that. And there is a relation here which we are going to use. And that relation says the following. So if I take a state here and I have an operator B, an operator B, an operator A, and an operator C, if I look at this quantity here, I can actually write it out, and you will see that this is the case when you put in the terms. So I have an A plus C complex conjugate times B times A plus C times psi and minus so if you just write these terms out, you will see that you get back to the expression which we have on the left-hand side. It's not so difficult to see that. So what we are going to do now is simply to identify A with the identity matrix. We are going to identify B with a Hamiltonian. And we're going to identify the C with minus I times a sigma of I divided by 2. So that means that I can now rewrite that specific term. If I look at the term which we have here, if I now plug in these expressions, I have a psi, and then I'm going to have the identity matrix plus I divided by 2 times sigma of I. And then it's acting on the Hamiltonian, and this is multiplied with I, the identity matrix, plus, wait, this should be, what did I do now? It's minus and plus. So this should be, sorry, I actually did it wrongly. So this should be, because we have minus, so this should be minus and minus I divided by 2 of sigma I multiplied with psi. And then we have minus, and then I have psi of identity matrix plus I sigma I divided by 2 Hamiltonian identity matrix plus I of sigma I divided by 2 times psi. Now, if we then, yeah. Okay, say it again.
The conjugates.
Yeah. So, yeah, sorry, I forgot to put that one because that should have dagger here like that and dagger here. Yeah, excellent. Thanks. Now then, we have some additional information which we can use now. So if we look at these matrices, these rotation matrices, this is something which is given by cosine. And if I now plug in the angle, so I would have I minus I of sine of phi half multiplied sigma I. If I choose an angle phi, which is equal to pi half, then this matrix, this rotation matrix of pi half is going to be equal to 1 over square root of 2 of I, identity matrix, minus 1/2 times sigma y. If I then insert that one into that specific expression, so if I then look at this term psi of identity matrix, which is equal to itself, so this is the term we are looking at when we are taking these derivatives, plus the Hermitian conjugate, obviously, which we're just leaving out here. This is something which I then can rewrite as 1/2. This looks like a complication, but you will see that this is something we can recognize quickly as the Hamiltonian shifted with a parameter pi half. So this is the same as pi half complex conjugate times h ri of pi half psi minus, and then I have psi, and then I have my ri of minus pi half, and then I have times h times ri of minus pi half, and multiply with psi here. Now, this quantity which you see here, this specific transformation here, is actually the Hamiltonian being rotated by an angle pi half. So that means that I can actually rewrite this term here when I add everything up as 1/2 and then multiply with the expectation value of h at an angle phi plus pi half minus the expectation value of h at an angle phi minus pi half. And this is normally what is called the parameter shift rule. So that gives us a recipe for calculating the gradients. So any Hamiltonian, which then can be written out in terms of chains of Pauli matrices, it's like the standard ones which we see now, and we operate on that one with the rotation matrices. All these operations here are operations where we can use the parameter shift rule. So if you, just to give you a small thing here, so let me bring back the screen here. So if we go back to the website, I mean the GitHub address of the course, so let's just bring that up here. So for this week, there are some additional slides which you can look up if you want to. I'm not going to go through them in a lecture, but if you now look into the PDF here, you will find an additional set of slides. Actually, there should be another one, which is called the parameter shift. So I need to upload that one. There are two additional set of slides here, which you can take a look into, which give you a little bit more information about the parameter shift rule. And also, in these additional slides here, I'm giving arguments for why you should measure on both qubits or on all qubits simultaneously. So if you go into Hunt's textbook, in Hunt's textbook, and as shown in the lecture notes as well for this week, the calculations are actually done in the basis of the first qubit, and then you're transforming all the operations to a measurement in terms of Pauli Z matrices. However, this has some complications and some drawbacks, which are discussed in these additional slides. And if I get time, I'm going to mention it towards the end of the lecture today. Okay, so this was a little bit about the parameter shift rule. So let's bring back the Jupyter notebook. So when we have this, we have now the gradients. And when we know the gradients, if we now are having many parameters, so we will typically have many parameters. Which we then can put in a common denominator, which we could call something like a phi 1, phi 2, phi 3, etc. Which means that we can set up a more and more complicated ansatz for the wave function. And a typical ansatz for the wave function then, if we have two qubits, and this is the case we're going to look at in more detail after the break in the Jupyter notebook. For two qubits, we would typically initialize the system like this, and then we could perform a Pauli X rotation with an angle phi 1. Then we could perform a Pauli Y rotation with an angle phi 2. We could do the same with the second qubit, and then we would have a new angle, an Rx of phi 3. We would then have a new state, a new angle, phi 4. And then we could entangle them by setting up a C0 gate. And this would give us an entangled state, which we would simply label as our state psi as a function of all these angles which you have here. Now, one of the things you can play around with in project number 1 is to make an ansatz for your system where you don't entangle with a C0 gate. So keep in mind that the C0 gate does not have any parameters. But what you would get now when you implement a C0 gate is that you have a final state here, an ansatz, which is entangled. There is nothing which hinders you of adding more such rotations and to have more angles. But however, this is something which I would call a pretty computational efficient ansatz. And in this case, you would have typically 4 angles, where each qubit now is represented by a random position on the Bloch sphere. That means that we would need the gradient of the energy with respect to all these angles. And this is the expectation value of the energy as a function of this h of theta. And then the way we would update these parameters, so for each angle phi of I, we have then an update where we have a phi of I minus, and there's a parameter alpha, which is the learning rate. And this is then multiplied with the gradient with respect to this quantity. So theta is a general container which contains all these angles phi of I. So this is what we need to set up. And that means that we need to set up alpha, which is normally called the learning rate, as a parameter. And obviously the results will depend on that learning rate. So here you can bring in, if you're familiar with machine learning, you know that you can update these parameters in many different ways. But the easiest thing, and which I recommend that we do in the project here, is that we simply just try to tune the learning rate so we get the best possible result. If we make it too large, then we may jump away from the minimum. If we make it too small, we may never arrive to the minimum. So tuning this parameter becomes important, because else you would have to calculate the second derivative of the Hamiltonian. And that involves many more calculations. So there's always this kind of compromise between numerical efficiency, computational efficiency, and the accuracy of your calculations. And in this particular case, it's actually cheaper to run for many of such parameters. So this leads to a standard gradient descent recipe, which I guess you're all familiar with. So we're not going to say much more about that. And typically, you would then run these calculations till the gradients typically go to 0. So that would be the classical stopping criterion which you would set up. So that was the second element, which we need to take care of when we are setting up a program. Then the third element is us making the calculations in the computational basis. So if we now look at the project 1, for the 1 qubit case, we are now going to need circuits for each one of the Pauli matrices which we have. So we need to calculate the expectation value of this ansatz which we have, where I'm now having 2 angles, phi 1 and phi 2, but I write everything in terms of a common denominator theta. So just to remind you of that one. So this is going to be given by a phi 1 and a phi 2 here. And then I'm going to have an identity matrix times some constants. I'm going to have a psi of theta. I'm going to have the Z matrix, which is pretty easy to calculate. And then I need to set up theta, and then I need a Hadamard. And then I have the Pauli Z, and then I have a Hadamard acting on psi of theta. So this is my original X. So that means that I have a longer circuit for that measurement. So each observable or each expectation value we are calculating needs its own circuit. And then finally, if we have a Pauli Y, then I would need to set up S times H, and then I would have a Z matrix, and then I would have H times S times psi of theta. Now, keep in mind that these matrices, H and the phase shift matrix, they do not contain any parameters. So the Hadamard is just set, it's just a simple matrix, but we would need now to complicate the operation. So that means also that when we are making physical measurements on these different components of the Hamiltonian, we need to perform additional operations on the state which we have parameterized here. Okay? So this is what we are going to discuss after the break, and we are going to show that by looking at the Jupyter notebook. And then we go back to the 2-qubit case and rewrite the Hamiltonian in terms of Pauli X, Y, and Z matrices, and then set up how we are going to do the measurements in a basis of 2 qubits. And we are not going to do that as it's written in Hans' textbook, where you measure on only one of the qubits, where you make a transformation. That is actually inefficient, and it's not the way it is done on actual quantum computers. So the code which you have access to for the 2-qubit case does it in the way you would run this on, let's say, one of the IBM machines or Rigetti's machines, etc., etc. We take a small break, 15 minutes. Okay, okay, let's do that. Now, there are 2 Jupyter notebooks which you have access to in addition to the standard lecture notes. So I actually wanted to single them out. So if you look into the folder with the teaching material, then the standard lecture notes, which we have been looking in a PDF format as well, that's the one which is week 6 here. But then I did not concatenate the Jupyter notebooks, and I preferred rather to have 2 separate ones. So the first one we're going to look at is the one for the single qubit case. So let me quickly say, no, that was the lecture notes. So this is the single qubit one. And the thing which we actually have, which is different from last week, is that now we implement the way you would actually do that on a quantum computer, except that you cannot run these codes on IBM's machine, for instance, because then you would need an interface like Qiskit to tailor it to their setup. And last week, I don't know if you had time to look at it, there are also 2 examples on how you can run the same Hamiltonians on IBM's machines. So feel free to play around with them if you want to compare what you are getting with the actual calculation on a real quantum computer. And then in that case, you will see that the measurements, if you look at the Bell states, for instance, it doesn't give you exactly 50%, but it may give you 49.5 or something instead of 50%, which should be the exact one. Now, if you now look at the gradient or the parameter shift rule, these are the gradients which we now need to evaluate for every parameter theta. And then we are going to make the measurements in the computational basis, 0 and 1. And these are the eigenstates over the Pauli Z matrix. So that means that when we look at the Z matrix in the Hamiltonian, that is going to be a direct measurement. When we have the X matrix, if we have a non-diagonal element, which then could be represented by the X, and if we have imaginary components, then we would have a Y matrix as well. Then we need to apply either a Hadamard gate or a Pauli shift gate, phase gate and a Hadamard gate, and then measure Z. So these are the basic elements which are now encoded into this Jupyter notebook here. And then we do something which is called a shot-based sampling for measurements. So finite measurements, they introduce a statistical noise, a statistical error. And each measurement which we're going to do yields either 0 or 1 with probabilities alpha squared and beta squared. And then we simply count the number of times we get zeros and ones. And then the expectation value is then estimated from the number of measurements. And we are going to get an error which scales like 1 over the square root if we calculate the standard deviation. So in the beginning here, this is just us. Actually, I just wanted to remind you that in the previous notebook, the one we discussed last week, then I used entirely SciP's optimizer. And there are many choices for optimization. But the thing which we're going to do now is to use actually a plain gradient descent with analytical derivatives. Okay? Any questions? Yeah? No, that is just plain pedagogical reasons. It's the easiest thing to implement. And clearly, this is something if you want to explore, let's say, using things like Adams to update learning rate, etc., this is something which you can add. I mean, in this case, you could also think of a stochastic gradient descent if you want to. So the optimization part, for those of you who are familiar with these elements from a course in machine learning, then you know that there are many ways by which you can update this learning rate in the plane gradient descent. Now, here I just use a plane gradient descent of plain pedagogical reasons, because that's the easiest thing to implement. But that means that your results will depend on the learning rate. So that becomes a parameter you would have to play around with, but you would have to play around with that one irrespective of whether you use, let's say, adaptive gradients, root mean square propagation, you have a plane descent with momentum, etc. So everything which you're doing now becomes a numerical experiment. And when you run this on a real quantum computer, it's actually a real experiment which you're doing. And that's pretty cute to think of. So we're actually using a physical system to simulate a quantum mechanical quantity like the calculation of the expectation values of the energies. So we have a shot-based sampling. So the beginning here is just calling different libraries. And then clearly the thing which you need, and the reason why I bring this up, and I hope you don't get offended if I give you almost the solution to the first exercises, but they can serve as a way to get started. So one thing you need to code is obviously the Pauli matrices. You need to set up the different quantum gates. And here, all the codes, I mean, I have not been thinking of speed. The way things are coded here is simply as close as possible to the mathematical expressions. And that's, again, for pedagogical reasons. Yeah.
When we enter the project, well, is it okay to make any measurements? The component?
Yeah, absolutely. Yeah. But you should also feel free to change the Hamiltonian if you want to, right?
Yeah.
So the kind of Hamiltonian which I'm suggesting, I mean, a slightly more realistic one. For those of you who took a course in many-body physics, we are going to look at the Lipkin model, but you could replace that one with other quantum mechanical models. The reason why we take some of these models is that you can rewrite them in terms of Pauli matrices immediately without having to transform a second quantized representation of a Hamiltonian via the Jordan-Wigner transformation. We will discuss that, the Jordan-Wigner transformation, a little bit later, but we don't need to think of that in project number one. So that will be the case if you have a more complicated Hamiltonian. So some of these kind of toy model Hamiltonians, like the Ising model, the Heisenberg model, Hubbard models, and so on, they are ready in a Pauli spin representation. So you can actually implement them in a pretty straightforward way. So what you would see here are typically the rotation matrices. I include the Hadamard. I have the S-gate, and then I have the transpose of the S-gate. So these are things which we would then need when we are setting up the Pauli matrices. And want to make the measurements in the Z basis, the X basis, and then the Y basis. Okay. And then there is a plain Hamiltonian, which I'm setting up here. In the project, we have put the Pauli Y part equal to 0. So here I'm just putting other parameters. And then here we just print the Hamiltonian. It's pretty useful to calculate the exact energies because that's the energy we want to compare with. And then I prepare the state, and you can see now that I'm doing a transformation here in terms of, and this is something which if you now look at this one, I'm actually doing rotations with 3 angles. But you wouldn't need that. So one thing you can play around with is the initialization and see how many such rotations you need on that single qubit. So this is always a very useful exercise to do, to look at the way you parameterize the system, because you're going to have a parameterized quantum circuit. So here I'm simply setting this up. So I have my psi 0, which is just state 0. You see that, 1 and 0. And then I perform a operation with this u on psi 0. So that is my new state, which I'm going to use to calculate the expectation values. And you can see now this is the exact ground state energy, which you have here. And my answer is simply that one. So I have not calculated this energy with the VQE here. This energy, which you see, is simply the one which comes from the call to a standard diagonalization algorithm. And in this case, it's just a 2x2 matrix. So this is really what we call a baby case. So what I have here now, and this goes back to the way we set up measurements. So here we have a measure in the Z basis. And you see now I'm giving in the state psi, the ansatz. And this is according to the number of shots I want to use. And then I calculate the probabilities. And we know that the probabilities simply have to be given by the projections of the 0 component and the 1 component. And then I do the sample measurements as a function number of shots. And then I simply count the outcomes. And then my expectation value is now simply the number of times I measure 0, number times 1 divided by the number of shots. So this is essentially the way we are going to set up these calculations. And that returns the expectation as a function number of counts. I do the same in the X basis. And in that particular case, I need to rotate psi. And I have to take the original psi, which is an ansatz with the rotation matrices. And then I have the Hadamard gate. And then I can measure that one in the Z basis. So I call back this measure in the C basis here. So I perform that explicit rotation. And then you can do the same thing with the Y basis. And you see now that what I have is an Hadamard gate times the phase gate times psi. And then I'm performing the same type of measurement here. And then I have the measure energy with these different shots. And you see now that they have the coefficients in front of the Hamiltonian. So if I go back, let me just go slowly back here. So my Hamiltonian now has 1 times the identity matrix, 0.5. So when we are running this with a real physical system, this would be actual so-called matrix elements, which express different types of integrals. So if you have a two-body system, this could be a two-particle Coulomb integral, where you would have specific values for these components. But now I just put in some numbers by random. And the same thing is what we did in project 1, where we just fixed these values as random values, just some given values, and then you would simply have to multiply them. So we calculate the number of the expectation values of these quantities, and then we have to multiply with these coefficients. So if we then go down here, you will then see that we are multiplying this with the coefficients which I have in front of the different matrices. And then I have my measurements in the X basis, Y basis, and the C basis. And then I simply collect that one, and that's a shot-based measurement, all measurements performed in a computational Z basis. Now, this is just a test. We don't need to look at that. We can see now the result as a function of number of shots. And the error typically decreases as 1 over the square root of n with n number of shots here. And you can also evaluate the standard deviation. So these are all quantities. The kind of post-analysis you can do is a typical standard statistical analysis. And when you list your results, you would also have to list the standard deviation, because you are calculating a sample mean value. Then we want now to implement the parameter shift rule. So till now we have not implemented. This is just us setting up the expectation values, and we are not optimized the angles. So keep that in mind. So the optimization part is the one which comes now. So the first part is us calculating the expectation values and preparing for that. But now we need to set up the parameter shift rule. So we need to calculate these gradients, and this is essentially done here. Then we look at the number of shots which are being set up, and then in here, we are now setting up the shift. So we have the plus value and we have the minus value. And these are the two quantities which we are going to return when we calculate the rate. Okay. So we need that one. So we done then we have the gradient descent optimizer, which is nothing but us doing a standard gradient descent here. And you will now see that when you do this, you have a gradient which you calculate here. And then this gradient is then multiplied by the learning rate, which comes down here. So this is the way we update. These are the parameters, the angles. And we have a learning rate, which is just a fixed parameter. And the results will obviously depend on that specific learning rate, which we opt for. So that's a standard plain gradient descent optimization. And we have defined that one. And then we run the VQE with different shots. And this is basically done here for the number of shots. And then we perform the gradient descent. This is that machinery. It finds the new parameters, has initial parameters, but just given by random values for the angles. This is the way we initialize the system. And then we find the optimal parameters by the VQ optimize, which we discussed a little bit earlier. And this is a result of the final number of shots. And then you can see that the energy which we are getting then keeps moving because we start with a random value, 0 iterations. And this is what you get after 90 iterations roughly. And this is with a number of shots equal to 100. And this is 100 iterations for the gradient descent part. So last week, this part which you see here, the shots per measurement, was absent because we just called a quasi-Newton methods in scientific Python, and that did the iterations and everything for us. Now we need to, since we are doing a plain gradient descent, you see now that our gradient is not exactly equal to 0 here with 100 shots. So if we increase with more, you will now see that the gradient, this is the case with 1,000 measurements. And this is what you actually do on a physical quantum computer. And you see now that you have the iteration. So this is the classical part. So just to remind you a little bit of that figure which we discussed before the break. The gradient descent part is actually this one, together with the parameter update. And that feeds back to the ansatz which we have. We find new angles, and then we would update the ansatz. And then we perform a rotation to the measurement basis, and then we do a measurement of the Foley strings. And now, as I said last week, we did not have this shots per measurement. And now you see that when we now increase, you see now that the gradient is getting closer and closer to 0. So the energy which we get now, the error is getting smaller and smaller. And then if you do 10,000, you will see that the gradient is getting smaller and smaller again, and the results are getting better and better. So if we now just scroll down a little bit here, you can, what I actually did, and this is something which I highly recommend. This is the boring part. And this is where, if you have the possibility, because the beginning which you saw here is as codes which I have written, but then when it comes to the plots and making nice figures, I actually punched in my codes to Claude Anthropic and just asked it to make nice figures. Because this is something which sometimes takes a lot of time. Actually, you would go through Matplotlib, look at the library there, find the kind of plotting which looks best. But then if you use, let's say, Claude Anthropic, it makes life much, much easier. And what I did was simply to ask it to plot the final energy as a function of the error, the number of shots, and the number of iterations. And I normally recommend using a mix of modern large language model tools, because that's something which can make your presentation much more efficient. And in this specific case, you can see now when you visualize, you can then look at the energy convergence versus shots. And you see now that the number of shots, I mean, you're roughly getting there, but you see that with many more shots, the curve for getting down to the exact result is actually much better. You can see the error evolution, and you can also see the gradient evolution, which is also quite interesting. And there's one thing which I didn't properly understand, and this is probably due to the learning rate. So you should play around with different learning rates as well. But you see how you can automatize it. And as soon as you have the basic elements, so the basic elements here, if we go back, the basic elements are you setting up the gradient descent. So this is just running the VQE in this specific case. So you have a gradient descent here, which you need to set up. And then if you go back again, you have the calculation of the expectation values. You have the gradient parameters, the shift rule. And then you also have the shot-based measurements. And you need to set up the measurements in the different, for the different Pauli matrices. And then clearly, when you're done, when everything is functioning correctly, I normally recommend, and this is what I do for my own research, I often have a large set of C++ programs, and which sometimes makes my work pipeline inefficient because I write to file, and then I have my matplotlib scripts, which reads everything. But now you can really automatize many of these operations here. Yeah, there are some other things which are also useful to look at. And that is the basis measurements, where you have the theoretical value, and you can look at the counts which you have. And this is a case with, I think that was with 1,000 shots. And you can see the number of counts you have. And it looks a kind of Gaussian for these kind of measurements. Clearly, the more shots you make here, the closer it will probably distribute itself around the mean. So this simply counts the expectation values of Z and X and Y as a function of the number of shots, and it simply calculates a number of cases when you got these specific values. And that can also be useful when you're plotting your results. Any questions so far? I mean, these codes contain more than we expect you to do in project number 1. But I mean, it can serve as a way to, I would say, how you can visualize some of the results. Yeah. Yes, and that's probably due to the, it could be probably due to the learning rate. So this is something, so these codes, they implement just a plain gradient descent, which clearly does not need to be the best one. Particularly, you have to tune the learning rate. So that becomes an additional parameter when you run the VQE, that since it's a hybrid algorithm, you may actually need to play around with different learning rates, as you do normally when you run a numerical experiment for a machine learning code or algorithm. Okay. So it roughly gives you the kind of things which we need in a project. Now, the thing I want to do now is to move to the 2-qubit case, because that's going to change a little bit the kind of recipe which we need to think of. So the 2-qubit case is basically the same, but now we need to make a experiment where we do the measurements in these spaces. So in Hunt's text, the way it's set up, and you will find that in the lecture notes for this week, is actually that you transform these different components of the Hamiltonian matrix in terms of measurements in the first qubit cases. This is not the way it's done anymore. So let me go back to the text for this week before we go into the Jupyter Notebook. So in project 1, this is a 2-qubit Hamiltonian which we have. So the way we've set it up now is that there is a non-diagonal elements, and you can now see that these non-diagonal guys here, this should actually be V of X. It's the same matrix elements which we plugged in. It could be different. But you see now that this block which you have here, this is actually a Pauli X matrix times H of X. And this block here is also Pauli X matrix. What you see here, on the other hand, is VC minus VC here. So VC and minus VC could be a Pauli Z matrix. But then we also have some elements along the diagonal. Now, if you use a software like Qiskit, Qiskit will actually take this Hamiltonian matrix and transform it immediately for you. So it does it for you behind the curtains. So you don't see exactly what is going on. So what you need to do is just some small tricks here where you can rewrite the matrix. So I'm just going and listing them here. And then that means that you can rewrite that Hamiltonian, which previously has a diagonal part, which is, so every one of these epsilons, they are the eigenstates of 0, 0, 0, 1, 1, 0, and 1, 1, the computational basis states. So these epsilon 1, epsilon 2, epsilon 3, and epsilon 4, they are the eigenstates of this part of the Hamiltonian, which we now are rewriting in terms of these different coefficients, which we have defined here, these ones. And then you see I have a tensor product of identity matrices 2 by 2. Tensor product 2 by 2, so that becomes a 4 by 4 matrix. Then I have the tensor product of a Z matrix times the identity matrix. Then I have I times a Z matrix. So in Hundt's textbook, and this is actually the way it was done before, then there are rotations of these matrices so that the Z matrix is the one which now appears for the first qubit. So this will be the first qubit, so this is pretty straightforward. But what you will be doing now is simply to make the measurement simultaneously on both qubits. But again, every term of your Hamiltonian here has its own circuit. So the C matrices, which you see here, are pretty straightforward. The same applies to this one. So you would actually make the measurement on qubit 1 here and qubit 2 here. But then the Pauli X matrix has to be transformed with 2 Hadamard rotations. Now, in the notes here, what you see now is that they're both tensor products. They have to be rewritten in terms of specific transformations so that you can perform the measurements in the basis of the Pauli matrices. That means that we need to, when we are going to make the measurement, so this P here is some kind of combination of the Pauli matrices, and the identity matrix is a unitary matrix, and M represents the gate matrix, which performs the measurement, often given by a Pauli Z matrix. So you can, if you think back to what we did for the 1 qubit case, then if this is a Pauli X, then we can have a Hadamard and a Hadamard. And that brings us back to a Pauli Z matrix, where we then can perform the measurements. So note that the derivations in the slides here, they actually follow Hundt's text. And there is an additional notes and also in the Jupyter notebooks on how you actually perform the measurements on both qubits. So the operations which you see here are essentially operations where we are going to transform these combinations of Pauli matrices into a Pauli Z matrix, as here, and then perform the measurement in the basis of the first qubit. Now, let me just take away this one and let me bring up the one I wanted to discuss a little bit. So there's some additional material in the lecture notes this week. And let me just bring that up here and share it as well. So there is a reason why you won't find this in the Jupyter notebook, and that is simply that I have had problems in using, there is actually a LaTeX package, which is called Quanti-KC, which allows you to draw quantum circuits. So I just wanted to say something. So if you look at the 2-qubit Hamiltonian, which is represented now in project 1 as a 4x4 Hermitian matrix. And what we want is simply to do that one by finding the ground state energy with a VQE. We choose a parameterized state. We estimate that one for measurements, and then we update the parameters as we did for the 1-qubit case. So nothing new here. But most devices which we're dealing with, they would typically measure each qubit in a computational basis. So a single 2-qubit measurement shot yields a bit string, which is now given by 0, 0, 0, 1, 1, 0, and 1, 1. So we want to map the outcomes to these eigenvalues, where these sigma z's here act on each qubit. So if you now look at the estimator for this one, this expectation value, which is 2 poly X, poly Z matrices. So that is something which you would sample the mean of the products of C1 and C2. So measuring both qubits in this Z basis, which is the one we are using, gives access to these correlations in one shot. There are some important arguments. So if you look at these probabilities of the outcomes, if you look at the C basis readout, what you would typically have then would be something like this for these different states here. So the first one, P0 and P01, these probabilities here, since it's qubit 0, you're measuring on the first qubit here. This is the identity. This identity does not do anything on the second qubit. But then you see that when I measure on the next one, so if my state is a linear combination of these, then I would get a minus here and also a minus for the next one. If I look at this one, this measurement, when I measure simultaneously, this is going to be given by this quantity. So in Hund's textbook, this one, this object here, the second one, is being transformed back into sigma z, tensor product with 1. And then you would perform just a measurement in one of them. So in practical measurements, with n shots and counts, this is actually what you evaluate. Now, there is something, suppose now that you measure only qubit 1 in Z and discard qubit 2. That means that you can estimate this one, but you cannot directly estimate the 2-qubit correlator without joint outcomes. And many Hamiltonians, they do actually include terms like that, which is what we have in the 2-qubit Hamiltonian. So without joint readout, you would need additional circuitry. And this is what in the textbook, so this is a kind of subtlety. In the textbook by Hunt, what they actually done is to add this additional circuitry so that you can calculate that expectation value. So what is common nowadays is to measure both qubits. And then joint measurements give you all these ones simultaneously from the same shot record. So this is something about the basic shot efficiency intuition. So if one measurement record yields multiple observables, you reduce total shots needed to estimate the energy to a given precision. There is also So when you now are setting up these kind of measurements, if you look at this measurement here, what you would have then, if you now use the single qubit, yeah. Could you say it again? Why?
Why did you write the book without?
Because that's a very good question, actually. So I'm not going to speculate why this is done, but this was the kind of approach which was used earlier. But then many of these modern quantum computers, they actually allow you to measure all qubits simultaneously. And I don't know why that hasn't been updated. I have not a good answer to that. But there are two recipes. So the recipe by Hund gives us many more longer circuit. But there are also some other arguments which I've tried to bake in here. So when you, I should. So what you have then with these single qubit identities, which we have seen for the single qubit case, then you would measure Zx on a qubit, you apply H, and then measure Z. So if you're looking at this one, you would have to perform this operation on that one, and you would do a corresponding operation on that one as well. And then for two qubit strings like sigma X, sigma Y, you apply the appropriate basic chain gates to each qubit and then measure both in Z. So that means the following. So if you look at what you would have to do then, when we have the ansatz, so this is the ansatz which we are looking at, then you would need to perform a Hadamard on the first qubit, if you have a sigma X here and sigma Z. So for this symbol here is actually a measurement symbol. And you see now that for the second qubit, which is this one, where we have transformed the states according to the angles, you just do the measurement. Whereas here you have to perform an additional Hadamard. And the same if you now have a sigma Y times a sigma Y, you then would have to apply the pace gate and then Hadamard gate on each of the qubits. So this is a two qubit case. There are some further considerations, and this is something which is a little bit deeper, and I put it up here more for the sake of completeness. So typically what we end up with for this two qubit case is that we have some parameters, which are just the values of the matrix elements. This alpha and beta, which you have here, are the different, so zero, sigma zero, just the identity matrix. And then I have the different Pauli matrices here. So if you look at the Hamiltonian, which we have in project one for the two qubit case, in that case, we have a sigma Z and a Pauli X matrix. We don't have the Pauli Y. So our Hamiltonian can then be rewritten in terms of a set of Pauli matrices. So this is a general expression. And when you're measuring only the first qubit, even after arbitrary pre-rotations, you cannot in general determine qubit correlators such as this one. So you cannot determine this expectation value for a generic interacting Hamiltonians. So what you will see here is that you prove formally that any single qubit measurement depends only on the reduced state of the one qubit. And you can then exhibit distinct states with identical row ones. So this is a density matrix, but you could have different two qubit operators. So here there's actually an example where you rely on single qubit measurements, which probably fails. So I invite you to take a look at this. I'm not going to go through that one in the lectures here, but I've added this as an additional material on why the measurement on all qubits is the standard way by which it is done nowadays. So in the, let me just stop this one. In the standard lecture notes, I hope this doesn't create confusion for you guys. But in the standard lecture notes, what I've done is actually to go through the way it's done by Hunt. So that means that when you look at this matrix, which you would have a Pauli C tensor product with the identity matrix, which will be part of your Hamiltonian. If you look at the Hamiltonian here, we would have a Pauli C times the identity identity times poly Z, tensor product, poly C with poly Z, and then we have a poly X and poly X. So this is our Hamiltonian. Now what you can do, so this matrix, when you perform a measurement on the first qubit, you see that this matrix gives us the correct eigenvalues for the first qubit, but not for the second one. If you then, well, I actually put in these experiments here, and you can see that it gives you the correct eigenvalues, but we don't get the correct eigenvalues if we perform the measurement on the second qubit. So this is something which is important to keep in mind, and why I don't like that approach. If you look at this one, which is also in the Hamiltonian, you can rewrite this one in terms of the swap gate. And what you would get then is that you would have a swap, and then I times Z times swap, and that gives you a Z times I. And then you can perform the measurement in the first qubit. And then you can do the same thing with the ZZ, which then would have a gate here, which is called a X10, which looks like this. And this is a matrix which you can use then to transform a poly ZZ. And when you do that one, this can actually, by this transformation, it can actually be rewritten like that. But you see, this becomes extremely clumsy because you get longer and longer circuits when you're doing this. Instead of making the measurement on all qubits simultaneously. And I've also put up different transformations here, and you will find similar ones when you look at. So this would be those which you would need if you want to follow Hund's textbook in order to make the measurements. And you can see that these are the gates that are relevant for the simpler 2-qubit example of project 1. And then you can get more complicated and look at all the possible combinations when you're setting up a general Hamiltonian. This becomes inefficient from a coding point of view, because if you go to many qubits, you see immediately that then you would need to transform many more of these matrices. And that's why this method is not used.
Actual physical
yeah.
computer, and would it be, is it way worse than actually at the same time? Like practically.
Yeah, no, it is, because you need many more operations in order to do that. Because every such operation is a new gate. So you're making the measurement longer and longer. And that means that if you have entangled states, you rely fully on these states living long enough so that you can run the computation. Yeah, let me just skip some of these things here. The thing I wanted to say a little bit about is the, or maybe we can switch that to next week. I can then present the final Hamiltonian, but take a look at what we have here, because this is a Hamiltonian which some of you are familiar with if you took many-body physics, and it's normally written in second quantization like this. Now, this Hamiltonian here, if you have a general Hamiltonian, you would transform this creation and annihilation operators by using something which is called the Jordan-Wigner transformation. And we are going to discuss that a little bit later. But the nice thing here is that you can transform these operators in terms of the so-called quasi-spin operators. And what you can do then is to introduce these quasi-spin operators, and they actually act as normal operators for the commutation relations of angular momentum. And I know that some of you who took the course in many-body physics, you've seen this before, and you've even done a project on it. And in that specific case, if you also introduce the number operator, you can rewrite the Hamiltonian like this, in terms of these objects here, which then can be rewritten as poly X, poly Y, and poly Z matrices. So like this JC can be rewritten as a poly C matrix. So that means that this is one of these kind of Hamiltonian systems where you can rewrite the Hamiltonian, which is wrapped out, written in terms of creation and annihilation operators. You can rewrite it in terms of spin-like operators. They obey the commutation rules for angular momentum. And then with that, you can transform every one of these in terms of poly X and poly Y matrices, which we are going to look at next week, how we do that. So there is some additional algebra here. So the Lipkin model in terms of this quasi-spin operator reads like this, and you can then, if you use the standard commutation rules and the Casimir operator, you can also simplify it further. And these are just some plain algebra, and you can actually rewrite it like this. So in the second part of the project, we are going to use this Lipkin Hamiltonian and set this up in terms of a case where we have total angular momentum equal to 2, which is going to lead to 5 times 5 matrix. And then we're going to set up a VQE solver for that specific problem, where we now have a set of poly X and poly Y and poly Z matrices. And this is what we will discuss in more detail next week. However, before we meet next week, I actually wanted to quickly, because I will actually go through that one as well. So this is the 2-qubit case, where we have tailored this to a Hamiltonian. If we want to make it more general, we can add poly Y matrices, but this is the one which we have in the project. So that means that we need now to set up these expectation values. And next week, I'm actually going to discuss these different terms which we need to code. So we have the 2-qubit poly operators, which we need to set up. We have the rotation matrices, we have the C0, and now we need to entangle when we're looking at a 2-qubit case. And then we have the Hamiltonian construction that you can see here, which is just pretty straightforward with just parameters chosen randomly. And then we have the VQE ansatz. And now you see that we have a circuit here where this didn't come out so well, but where we are entangling the states. And these are things which we will discuss in more detail next week. And we are also going to discuss in more detail the Lipkin model. So by the end of next week, we should have all the elements which you need for the project. But feel free to use these code examples. Questions before we stop? I hope I'm not throwing too much information at you guys. There are some smaller subtleties which pop up, but hopefully when we discuss them, both in the lab sessions and also during the lectures, you will hopefully see the wood for the trees.